All right, this is a video discussing the idea of vector spaces in general. Okay, a vector space is a collection of things we call vectors together with a field, don't worry about what field means here, of the real or complex numbers, okay, that satisfy a bunch of conditions. Okay, so we're working over the reals or sometimes the complex numbers. Okay, vectors we will represent like we usually do with small Latinic letters with bars on top. Okay, all right, what conditions have to be satisfied in order to have a vector space? The first condition you have to have is closure. Okay, what does this mean? Actually, there's two types of closure here. The first type of closure, oh, by the way, the upside down A means for all. Okay, so read that as for all vectors u and v of your vector space. Okay, u plus v has to also be in the vector space or the set of vectors. Okay, okay, so the vectors are what we say is closed under vector addition. Okay, so the sum of two vectors is always another vector in your vector space. Another thing here, for all scalars A, okay, so that's read as for all A element of the real numbers or belonging to the real numbers. And for what? For all vectors U in your vector space, the scalar multiple A times U should also be in the vector space, or I should say must be in the vector space also. So we would say it's closed under addition and scalar multiplication. Okay, so you shouldn't be able to take two vectors and add them and get something that's outside the vector space. The same thing with scalar multiples here. Better be back in there. Okay, so another condition I'm calling 2 here is commutativity. Okay, if I have any two vectors in my vector space, I should be able to add them, right? And in addition here for commutativity, it shouldn't matter what order I add the two vectors in. So u plus v should be the same thing as v plus u. Okay, you should recognize that name from basic algebra. Okay, commutativity of vector addition. Also associativity. Okay, they could consider three vectors here, u, v, and w from your vector space. Okay, if I go u plus v first and then add w afterwards, I should get exactly the same thing as what? U plus v plus w added first. Okay? All right? So just basically I should be able to shift these parentheses around. What this ultimately means with associativity is if I'm just adding a bunch of vectors, I can basically ignore parentheses altogether. Okay? Here's another property we're going to need here. You're going to need something called the additive identity vector. Okay, so additive identity, there has to exist a unique vector, and I'm putting a 0 with a bar on top, so that's my additive identity. That has to exist in the vector space and satisfy the condition that what? Whenever it's added to any vector u, I get that vector u back. Okay, so this holds for all u in your vector space. So this has got to be a unique vector. There's not going to be more than one of them here. Okay, some books you could write this backwards also, but remember we have commutativity of addition anyways. Okay, we have commutativity of addition. How about additive inverse? Okay, you probably know what that means. Okay, now for each vector u in our vector space, there must exist a unique, okay, so just one, a unique additive inverse for that vector, which we're going to designate this way, negative u, okay, such that when you add u and negative u, you get this additive identity, or the 0 vector, what we're calling the 0 vector. Okay, okay, this is also unique here. Okay, some people would call that redundant because you can actually prove from this condition that the vector 0 has to be unique, but I'm throwing it in here for emphasis here. Okay, scalar associativity. Okay, for all scalars, a and b, and the real numbers or possibly the complex numbers. So this is contextual here. Okay, I'm just assuming it's a real vector space here. So for all scalars a, b, and the real numbers, and all vectors u in your vector space, if you go the product ab times u, you should be able to go a times bu. Okay, so once again, you should be able to shift those parentheses around. Okay, alrighty. But this is dealing with scalars this time instead of adding vectors. Scalar distributivity. Okay, remember what the distributive property means? Okay, once again, for all scalars a, b, and vectors u, okay, if I go a plus b and then take that scalar and multiply it on u, I should always get exactly the same thing as a times u plus b times u. Okay, so you recognize the distributive property there from basic algebra. Okay, vector distributivity. Okay, for all scalars a and vectors u and v. Okay. A times u plus v should be au plus av that I've got there. Okay, so these should be pretty intuitive here. One last property, you've got to have this scalar identity multiplication property. For all vectors u, if I go 1 times that vector, I should get that same vector back. Okay, so the scalar 1 is acting not just as a multiplicative identity in the real or complex numbers, but also over the vectors. Okay? Alrighty. Let's look at some examples of vector spaces, ones you're very familiar with already. Okay, the vectors in R to the n, right, Rn, together with the real numbers forms a vector space with our usual addition and scalar multiplication. Okay? In fact, I take a even more concrete example here. For example, R squared. Okay, suppose a, b are scalars, and I've got vectors u, v, and w like I've written here. And I define this with u plus v is just what? Adding these two component-wise, so that's u1 plus v1, u2 plus v2, and then the scalar multiply the scalar on each of the components here. au1, au2, okay? This defines a vector space. Okay, this ends up defining a vector space. I am not going to go through and show that all of these properties are satisfied. Okay, all 9 of them that I have written here. But in fact they are, and I think you can probably see that pretty simply. Okay, so, and this is just not for r squared, but r to the n, right? Or rn, however you like to say that. Okay? So the n tuples. Okay? Here, so let's take a completely different type of vector space, because you're really used to seeing this kind of stuff already. Here, let's take something rather different here. Okay, just imagine the set of functions. I guess I should have given this a name, the set f. Okay, give it a cap f or something, of functions from the real numbers into the real numbers. Okay, that's the only demand I'm making. Okay? Consider all those functions from the real numbers into the real numbers. So a real number goes into the function, a real number pops out. So I'm assuming here the domain is all real numbers, okay? The range for any particular function is some subset of the real numbers. Okay, together with the real numbers and with the following addition and scalar multiplication properties, okay? Or definitions, I should say. Okay, you remember back in college algebra, or maybe even before, when you were adding two functions, you just basically did it pointwise, right? You talked about the sum of two functions being what? Just the sum of the two values of the functions at each value of x, okay? That gave you a new function, okay? You can see that clearly this function is what? Also a function with domain R and a range in the real numbers. So this is definitely, we've got closure here, right? Okay, we've got the closure property. And how about a scalar? If a is any element of the real numbers, okay, if I go a times the function, so I'm defining a f1 here, I'm just going a times the value of the function at each value of x here. And that would define a new function here, right? Okay. That's still going to be a real valued function, right? From the real numbers into the reals, okay? So we definitely have closure here. This actually forms a vector space What I discussed here under these definitions was basically just the closure properties. But all this other stuff, I think you can see, is actually going to hold. All these other properties are going to end up holding as well. Okay? So this is vector space also. Okay? This is a really strange one, maybe, given your experience at this point. Okay, the set of all continuous functions from the RILs into the RILs. Okay? Is the sum of two continuous functions also a continuous function? Yeah. How about the scalar multiple of a continuous function? Is that still continuous? Yep, it sure is. So you've got closure again, and once again, all these other properties will hold. Okay. In fact, that would be an example of a subspace of this space. Okay. I haven't defined what subspaces are yet, but I'm about to. Okay. Before I do that, though, let's talk about a couple quick things that I'm going to use when I talk about subspaces here. And these are useful anyways. If I go 0, here's my first proposition. If of course, 0 is an element of the real numbers or the complex numbers. If I go 0 times a vector, I claim that I get the 0 vector. That is the what? The additive identity, and that holds for all u in the vector space. And here's going to be my proof of this. You could make this a little longer if you wanted, but basically this. If I go 0 times u, and then add that to u, okay? That's really 0 times u plus 1 times u. You remember the identity multiplication property. Scalar 1 multiplies on u, I get u. Okay, so I'm going to add these two, so these two are equal. So then what? Okay, the scalar distributivity part says I could actually go 0 plus 1 times u, 0 plus 1 times u. But what's 0 plus 1? Well, it's 1. And so I've got 1 times u, but what's 1 times u? Again, from the scalar identity multiplication property, that's u, right? So I've got what? Some vector plus u is equal to u. So this vector has to be what? Because there's only one of those, it's unique. That actually has to be what? The additive identity. Okay? And likewise, if I go -1 times u, okay, any vector u, I actually get the additive inverse. This is one of my justifications for writing it as -u here. This holds for all u in the vector space. Let's go ahead and it's a property. The proof of the property is, or the proposition is similar to the one above. Suppose I go u plus -1 times u. That's what, again, 1u plus -1 times u. Again, scalar distributivity, I'm going what? 1 plus -1 times u. That's really what? 0u, which is 0 by the proposition above. Since these two, what? Added together to give me the additive identity, Ips must be what? That guy's got to be the inverse, okay? Because it's unique there. Okay? Alrighty. Those are good things to remember. Subspaces of a vector space. Suppose that I've got a vector space, vector space V, and I've got some subset of that vector space, okay? The set U is called a subspace of V if U is a subspace in its own right, or a vector space, I should say, in its own right. It is a subspace, vector space in its own right, okay? So you've got, in some cases, what? Vector spaces inside other vector spaces, okay? We'll give you some quick examples here. Okay, something you're used to. Suppose I'm dealing with R cubed, right? Just the, what, 3 vectors with real components there. Okay, let's just consider a subspace here. This is going to be really easy, okay? Let U be the set of all vectors of the form. Okay, so when I say vectors, there's going to be 3 vectors. But they're going to be the 3 vectors of the form A, B, 0. Okay, so the what? K component, or third component, is going to be 0. A and B is allowed to run through all the real numbers. Okay, can you see that the U is actually what? A subspace? Okay, that this is a vector space in its own right. I could go through all the properties of a vector space, right? And this will satisfy them. The 0 vector, by the way, is included in here because I've got what? 0, 0, 0 here. If I let A and B both be 0, I've got the 0 vector in there. Okay? By the way, I say this, and just think about it here. This is essentially what? The vector space R squared, right? Okay, we often did this like in Calc 3, where we used I, J, and K, but if you went down into 2 dimensions, you just what? I and J really didn't change. You just ignore the what? Third dimension, the third component here. Okay? It's essentially the same vector space as R squared. Okay? It just looks a little different here. Here's another example. Okay, suppose V is R squared. Okay, I'm going to take the following subset. Let's take all vectors of the form A, where A is allowed to run through all real numbers. Okay, notice that once again this includes the 0 vector. Okay, this is what? The subset of all vectors parallel or anti-parallel to the vector 1, 1. See, these are all just scalar multiples of the vector 1, 1. Can you see that this is also a vector space? Okay, I threw this in red here. It's together with the 0 vector because some people don't like saying that the 0 vector is parallel or anti-parallel to another vector. Okay, it is a scalar multiple. In some people's formulations, you could say it's sort of degenerate parallel. Anyways, okay, this is also a subspace, right? All the vectors parallel or anti-parallel to this vector, okay? You could run through and you could do the scalar addition and see it's closed and so forth. So scalar multiples. It satisfies all these properties, okay? Oh, I had that other example too, didn't I? Set of all functions, right? A subspace here would be the set of all what? Continuous functions, okay? All right. That would be another subspace. Let's talk about a quick theorem here. Okay, and I'll leave you with an exercise. It's very easy here. Okay, here's our theorem. Let V be a vector space over the reals or complex numbers. U is a subset of V is a vector space of V if and only if, what? The 0 vector's in there. It's closed under scalar multiples. Okay, and it's closed under what? Sums. Okay. By the way, the 0 vector actually has to be contained in this because I showed what? 0 times any vector is the, I is kind of redundant here. But the point is basically that you've got a subspace, what? So long as you, of another vector space, you've got a subspace if you've got these closure properties. That's all you really need to pay attention to. Why is that? You know, I didn't give a proof of the theorem, but we can just chat about it real quickly. It's not really very difficult here. When you come back here, closure is basically all I have to worry about. Now, I've got the additive identity I needed in there, okay, but I've really got that. I mentioned that already. You need that in there. But that actually occurs, as I stated, when A is 0. But anyways, we throw that in, okay? But you see that commutativity is already inherited from the vector space V, okay? U has the property that the sum of any 2 vectors, it doesn't matter what order you add them, you get the same vector, right? It's commutativity because this already holds for all vectors U and V in the vector space V, the original vector space. So this is inherited. This is inherited, associativity. Okay, this we just mentioned. Additive inverse. Okay, this is actually what? How do you know there's an additive inverse in my subspace? Because I've already showed that what? -1 times U is what? The additive inverse. Okay? And so if I have closure under scalar multiples, I'm guaranteed to have had what? The additive I inverse for each element in my U, in my set U. Okay? How about scalar associativity? Well, again, that's an inherited property from the original space. Scalar distributivity, inherited. Vector distributivity, inherited. Scalar identity multiplication, inherited. Okay? So basically, this is all we need here. Actually, only these two. Even that's a little redundant. Okay? All right? So if it's closed, another way to think of it is if it's closed under linear combinations. Okay? If it's closed under linear combinations within another vector space, it is a vector space in its own right, In other words, a subspace. Okay, here's an exercise for you. Suppose my original vector space is order the n. Okay, and let's say I've got a collection of, say, k vectors from the sample space. If I say U is the span of those vectors, U1 through UK, I claim that this is a sample space, or this is a subspace. Can you prove that? Okay, that's an exercise for you. I want you to be able to prove that. The proof is actually very easy. You just go through, and basically what do you have to do? What would you do here? I would use the theorem right above. Okay, use the theorem right above. Remember what the span means. Span is just the set of all linear combinations of these vectors. Okay, well, there you go. That should be an easy introduction to vector spaces and subspaces. All right, we'll talk about some specific subspaces and basis and stuff in the next video.